Hello and welcome back. In the previous session, we saw in the toy example of Andros Brownworth, uh, from whom we are uh, happy to borrow the toy blockchain. So you saw in that example how a block is created from a data and how a hash is generated given a certain constraint, in this particular case, 4 leading zeros, by mining the right nonce. And in reality, you know that one block consists of many data or many transactions, not just one data. But for this toy example, we'll stick to only one data. We also said that what what form the data will take in a blockchain. Um, we will explore that. For the time being, we just gave a dummy data, which is quick brown fox jumped over the lazy dog. We also know that whatever be the length of the data, however big the data may be, the size of the hash will not change. The size of the hash in this particular case is a 64-bit hash, which is typically used in the SHA-256. So you see that irrespective of what the size of the data is, I can go on writing any length of data, any type of data, whether it is the form of a text, in the form of a table, it's form of an image, it's form of a video, whatever be the type and the length of the data, it will always generate a hash that is of 64-bit. Now, this hash is not valid anymore, as you can see from the fact that this block has become red. We need to mine this block again. Let us mine this block again. And once you mine this block, you see that the system has found a new nonce, and this new nonce has given a new hash which has the 4 leading zeros. However, it is still the same length of the hash, 64 bits. So this ensures that whatever be the size of the data, the hash is always of the same length. This is a very, very important utility in the context of blockchain. Again, we will see all of these things when we discuss the science of blockchain. We will now create a blockchain from these blocks. So let us go to this blockchain module, and this time we are going to create a set of blocks which will act as a chain of blocks. In this case, instead of just giving any arbitrary data like the quick brown fox jumped over the lazy dog, let us say that there is a transaction happening between parties, and we'll just write this transaction in this format: A to B $10. I mean, A is giving B $10. B is giving C, B to C $8, presumably from the same $10 that B has received from A. C is giving to D, C to D $6, presumably from the same $8 that C has received from B. And D to E $4, and E to F $2. So we have crudely represented a monetary transaction. This is not how typically it is represented in a Bitcoin or any other blockchain for that matter. As I mentioned, that the way data will be represented in a blockchain will vary. It will depend on the use case that we're talking about, and it is more complex than what we're seeing over here. But for the time being, to understand the concept of blockchain through this toy example, we will use this kind of a data. As you have seen, that this entire thing has become red. All the blocks have become red because none of the blocks are providing a valid hash. Now, the hashes are no longer valid, and hence all of them are red. Now, what we'll do is we're going to mine each of these blocks one by one and make a valid hash so that the block becomes valid. That a valid hash means that it complies with the constraint provided by the algorithm, which in this case is a certain number of leading zeros. Let's mine this. So now you have a valid block with a valid hash of 4 leading zeros with a nonce value, which is different from the previous one. So the computer has found out the nonce value by brute force technique and found out this hash. So similarly, we'll just go on and mine the next one. As you can see, it takes some time to mine the block because it is applying brute force method to find out the valid nonce. And the next. And the next. And the next. So now we have a valid set of blocks. Now let us understand some interesting things. One new column or new field that has been added, which is the previous. Now this previous means the hash of the previous block. So if you see that the hash, the previous, the value in the previous field of block 2 is equal to the hash field, the value in the hash field of block 1. That means every block contains the hash of the previous block. So in this way, if I know this block, I would be able to figure out what is the block that is preceding this block. So I know this is the previous hash of the previous block, and I will find out which block has hash which is equal to this 4 zeros and 529. This is this block, so this block must be prior to this block. Okay, and similarly, block 3 is prior to block 4. If you remember that one of the characteristics that a blockchain should demonstrate is the concept of provenance, because provenance ensures is one of the elements that builds trust in the system. Now you see that how these blocks have established provenance by incorporating the value of the previous hash in each of these, the hash of the previous block in each of these blocks. What is also interesting to note that if you change the value of any block, let's say D later on decides, maybe with a malafide intention or by mistake, that he or she actually paid $6 to E instead of $4. Now see what happens. Moment D tries to change this to 6 from 4, the blocks subsequent to D, this particular block, which is block 4 and block 5 become inconsistent. So it is easy for anybody to figure out that something wrong has happened in block number 4, because of which block 4 and block 5 have become inconsistent. So this also results in immutability. If you notice now that if you have to correct these blocks, that means if you have to go back and make these blocks consistent, these two blocks, block 4 and block 5, have to be mined again. To mine again, it can be corrected. It can be corrected, but that will take an effort. That will take an effort on part of the party with a malicious intent to correct this block. Later on, we'll see using the distributed function how this can be made more difficult so that such changes cannot be done, or it will become almost impossible to make. Let us change it back to our original values and make it consistent. Also, will notice that further down a block is, let's say I try to make, A tries to make this change over here, 12. Further down a block is, in the chain of blocks, more difficult is it to make a change. So now, since A, this block 1 is further down, further upstream in the chain of blocks, it's more difficult to make any change in block 1 compared to, let's say, making any change in block 4. Because now, whoever has made a change in block 1 has to make changes, has to mine all the 5 blocks to make it consistent. So deeper a block becomes, older a block becomes, more immutable it becomes. So this immutability, as you know, is also one of the important characteristics to build trust. So we'll go back to 10 over here, and all this thing all becomes consistent as of now. So you've seen that how the chain of block by this provenance of previous blocks has built a provenance, ability to trace back a block from its subsequent blocks, and also how it incorporates immutability by making it difficult for anybody, any malicious party, to change any value on the block post facto. We will now discuss about this concept of distributed, and the distributed concept, what we are going to do is we are going to have the same set of blocks in multiple nodes, and this will make changing any value in a block more difficult. We'll look at the distributed nature of the block check in the subsequent session.